Hello everyone. In this video I'm going to talk about the differences between a statically determinate system, versus a statically indeterminate system, or body. Alright, so remember, for a body to be in static equilibrium, and that was the case when the acceleration is 0. And for us, we're going to consider static equilibrium to be not moving. The case of constant velocity is kind of more of a mathematical case. It's typically hard to get in real life, so we will not be talking about those. Static equilibrium means it's not moving. We're going to apply two vector equations, or we can apply two vector equations. Sum of forces in 3D, this is going to yield 6 scalar equations. All right. Sum of the forces in the x, sum of the forces in the y, sum of the forces in the z directions. So the components of the force vector are all 0, and likewise the components of the moments in all 3 directions are going to be 0. And in 2D, this gives 3 scalar equations. So there's only, say, an x and a y direction. There's no z direction. So we can only sum forces in that direction. In this case, there's only moments rotating out of the plane. So there will be only moments in this direction. All right. So I'm going to say if all unknown forces or moments, so these are your interactions that you apply to the free body diagram. If some of them are unknown and you can find them, can be found by applying equations of equilibrium So if you can't do this, then the system is statically determinate. So that there will be no unknown interactions on the body. If not, then the body or the system is statically indeterminate. Okay, so unknown forces typically come from, so these things typically from constraints or fixtures. Okay, so let's take a look at an example here. So let's go back to the good old cantilever beam. We have a beam that's fixed into the wall. I'm going to apply a force at an angle here. So this force is known. And I'm going to draw this force in components in this direction. So these are known. This will be y, let's see. So we're going to give ourselves a reference frame coordinate system x and y. So z will be on the page. So here's y, here's x. Okay, so our free body diagram would be as follows. If I draw, here's a side view. I'll just take this force which is applied at an angle, at some known angle, break it into components. So I'll have applied at some point Fy. At some point I'll draw it just down here because I don't have room up the top. Okay, so those are known forces. Let's neglect weight. Let's say, but using our engineering judgment, we say the weight is small, say relative to these applied forces. Now looking at the boundary condition, I'm going to assume fixed that wall. So we recall that means there's no translation and no rotation. To enforce that, I have a force that's going to hold it in place here. This is unknown. And I'm going to apply a moment, right? So this body, this beam, I'm pushing down on it at an angle, is going to want to rotate. If I say it's fixed, then there's no translation, no rotation. So to get that condition, I have to apply a moment. And I'll call this point A. All right, so in this case, Rx, Ry, right, known, so those are forces that I'm applying to the beam. I know what they are. The system, this beam is in static equilibrium. It's not translating or rotating. And so there are forces and moments being applied from the wall to the body, which ensure that. All right, so let's apply the equations of equilibrium and see if we can solve for these three unknowns. So recall we're going to sum the forces in the x direction. So that's going to be Rx plus Fx equals 0. We'll do this in the y direction. We have Ry. So we're taking scalar components. Minus Fy. All right, so pretty straightforward here. Summing the moments, we'll sum the moments about point A in the z direction. Okay, we'll call this direction positive. So this is an unknown moment, right? There's an unknown moment that's applied to the tip. These forces, the distance from the axis, that we want to determine the moment of 0. So these do not generate any moments, Ry and Rx, even though they're external forces. These are external forces. They generate a moment. This is going to be in the opposite direction, Fy. Let's say this position from here to here is L. Fx is an external force, but the angle between it and R, which is R, remember, is the distance or the position vector from the point to the tail of the vector. The angle between those two vectors is 0, so it does not generate a moment. So 3 equations, as we expect from 2D equations of equilibrium. 3 equations, 3 unknowns. Sorry. You can solve for those unknowns. In this case, it's pretty trivial. You can just do this by inspection. So this system is statically determinate. All right. So let's change this problem a little bit. And let's introduce another fixture. So let's take the cantilever beam again, fixed to a wall, but now at some intermediate point, let's sit it on a point. So when I push down on it, again, I'll break this down into known forces in the x direction, Fx and Fy. I'm going to run into this fixture here, which is supporting it. In that case, when I draw the free body diagram, and I'll define my coordinate systems again, we're in 2D. So the free body diagram is as follows. Now I have an unknown force support here. I'll call support force Y. At this point I know push downward. This is attached to the wall, so again I have the wall reaction forces, which I'm going to call Rx and Ry. And I'll have a reaction moment MAZ. So it's pretty clear when we apply the equations of equilibrium that we'll see a different set of unknowns. So in this case we add a known force, some forces in the Y vertical direction. So we have this reaction force. Now we have this new support force. And we have the force pushing down. And again we'll sum moments about point A. These would be in the Z direction. So we have MAZ. Again, Ry and Rx do not generate moments about point A. Let's call these all forces. This constraint force, or this reaction force, does, we'll call this distance L2. This is going in the opposite direction. It generates a moment. We'll call that L1. So here we have how many unknowns? We have 1, 2, 3, 4. So 4 unknowns, 3 equations. So this problem is statically indeterminate, meaning you cannot find values for all the unknowns using just the equations of equilibrium. In this case, you actually will have to, if you want to find this for us, we'll need to consider deformation. So these class of problems we will not be looking at this semester. So we will just be focusing on statically determinate systems. So let's note one thing. By observation, in general, you can see whether a system is statically determinate or indeterminate by imagining if you took away one of the constraints, would the system still be in equilibrium? So again, we have a beam, it's fixed to the wall, there is a vertical support here. I'm pushing down on it with some force in this direction. Imagine if I took away this support, essentially removing this as an unknown, is this system going to be in equilibrium? So if we took this away, we're back to our good old cantilever beam. So yes, this problem then would be statically determinate. So by having this additional constraint here, we see that the problem is statically indeterminate. Likewise, if we change this end to, say, another joint such that it is not applying a moment, so no moment. All right, so we're changing the problem. This is a different problem now. We've removed sort of the moment, the magic hand that the wall is holding on to the end of this. If we reduce that, then we reduce this number of unknowns to 3, and then we're able to solve for the 3 unknowns. So by reducing the constraint at the wall, we go from an indeterminate problem to a determinate problem.